Right, so we're starting slightly late, so apologies for that in the best way of the world. We had a slight few technical issues. So I'm Adam Taylor, and for the last few years I've been working predominantly with the Zinc and the Zinc MP-SOC and FPGAs. I've been writing about these on the MicroZ Chronicles, so if you ever fancy getting to sleep one evening, you can take a read of these. But, oh, come on, that must work now. Eventually. So I think actually Dan might have talked a lot about this, so I'll briefly cover these ones so we can all get to the bar in time. But for those, what's going off with this set of slides here? For fuck's sake. No, it's okay. I'll just press the buttons on the thing. It's easier than that way. Okay, so for those unfamiliar with the Ultra96 board, there've been a few all week on the AvNet stand. There's some really great examples running on there. It contains a Heterogeneous Soc, which is the Zinc MP-SOC ZU3EG. I'm going to talk about that a little bit more in a little while, but initially, just to give you some context of what it is, it contains 2 GB of RAM. We've got the SD card on there, and obviously it contains the 96 board format in terms of the consumer specification. Now, generally, when we develop these things to get the best use of the Wi-Fi and everything, we're going to be using a PETA Linux type build on there. So PETA Linux is a build that comes from Xilinx that allows us to develop that flow, but it's not actually a distribution. It's just a build chain that allows us to actually get Linux running on our system. So it's a little unique, the Zinc MP-SOC, in that it contains a processing system and programmable logic. Now, obviously, you probably had this told in the last session, but in the processing system, obviously, we've got the quad-core A53 processors. We've got the R5 processors. They're really quite powerful. And it's really quite useful for a lot of industrial Internet of Things, embedded vision applications. And we have, obviously, the programmable logic. Now, programmable logic is really good for accelerating functions. It gives us a really good performance improvement. But there's also some other good uses for it, such as interfacing, which we're going to look at. And between the two, obviously, as Dan alluded to, actually, we have AXI interconnects. So we have master and slave interconnects for the AXI interface in both directions. We have fabrics and clocks. And then we have what I've currently called other down the bottom. But we have, obviously, interrupts from the PS to the PL, PL to the PS. And also, we have a lot of debugging interfaces that go between there, such that we can, if you want to, because this is obviously, when you get to debugging your application, this can be quite complicated. So you've got interaction going off in your programmable logic, you've got interaction going off in your system on chip, your processor side of things. And you can put integrated logic analyzers in there, let the integrated logic analyzer trigger and actually breakpoint and stop the software running, so you can actually see what the interaction is between the two. Or you can do it the other way. You can hit the software breakpoint and you can actually make it see what's going off with the logic analyzer. So it's quite a useful application. So I'll flick through these slides quite quickly, actually. But obviously we've got the ARM processor code, we've got the MAL, we've got the A5. And we've got a lot of connectivity interfaces as well, which are really flexible for when we want to talk about breaking out sort of different standards. So you can use a multiplexed I/O to bring out maybe an I2C or a CAN or something like that. And you can configure this all via Vivado. Now there's some lesser known but quite useful subsystems in here. Everybody always talks about the R5 and the APU, but actually there's a configuration security unit in there, which is also very useful if you want to do cryptographic things, if you want to do some security work. You don't have to accelerate cores into the programmable logic. You can use these functions in the CSU, and you can just DMA data, large chunks of data into or out of them via the AXI interconnect from your APU or the RPU, whichever application needs to do it. So it's quite a useful little application, so I thought I'd mention it here. But the first one is actually, so I'm assuming that most people in this room are software engineers. Are not too familiar, with the exception of you guys over there and yourself there. So most people are fairly unfamiliar with programmable logic. So it really begs the question of what is the benefit of programmable logic, and it's really there's a number of applications actually for it. So the first one, as I mentioned, with the 96 board format, obviously we have the high-speed connector and the low-speed connector, and they're connected to elements of the design, mostly to the programmable logic side of it. And we want to really be able to have flexible interfacing in that. And programmable logic gives us that. Pretty much with if we put a PHY on the board, if we can get the right PHY on there, we can get the programmable logic to do that interfacing. So we get really any-to-any interfacing capability, which is quite useful when we want to start working with maybe some bespoke or some legacy interfaces, or we want to add in multiple types of interface when we're kind of limited with what's supported otherwise. Then, of course, there's always the traditional approach, which is the programmability, the acceleration that comes when we accelerate something from the PS into the programmable logic. And that's mainly because one of the key things we do is we remove the bottleneck of the DDR. So as opposed to actually having to transfer elements of processing between the processor into the DDR and back out of it again, so you're competing for resources, actually it's running straight through the programmable logic, so you've got a traditional pipeline that goes from the input all the way through to the output, so it's much more deterministic, much higher performance, and it's just a lot better. For the right application, it's a lot better. But what you need to do is need to think about what we want to move from the PS to the PL. So there's a range of things that are quite popular these days. There's a number of verticals, really, the Internet of Things, embedded vision, machine learning. Actually, what I tend to see, really, as an engineer on the ground working with a lot of customers, is these things all kind of merging together into a number of applications anyway. And if you were to start developing for programmable logic, if you come from a software background, it can be quite difficult. You've got to understand the concept of clock domain crossing, clocks, processors. When you look at your processors in your VHDL, they all run at the same time. They all execute at the same time, apart from contents within them which execute sequentially. So it gets to be quite a mind thing for if you come from a traditional software background. So it's quite difficult to do that and take advantage of what's in the PL there. And actually, a lot of times when we develop embedded vision systems or machine learning systems, you start out with a high-level model in maybe MATLAB or C, and actually there's a big gap then between where your model finishes and where you start working with VHDL or Verilog, and you have to kind of fill that in and start working with it. So when actually we start working with the Ultra96, one of the first things we can do is, actually it's very simple. If we use Vivado, we can use IP Integrator. So what you see up here in the box there, where it says Zinc Ultrascale in it, that defines a processing system. So that's contains the APU, the R5s, the multiplexed I/O. So you can double click on that and it opens a nice little GUI that you can configure that, the interfaces between the processor system and the programmable logic that you want to enable. So that's all hard silicon, but what you're just enabling options that are in there. And then everything else around it actually sits within the programmable logic, the FPGA side. Now, what's really quite good about this is actually Xilinx give a lot of IP. So you can literally just start there. And if you want to create an embedded vision system, you can literally start there, just pulling IP in. And you can simply create an IP vision system without having to write any code of you. And all you've got to do is drop these boxes in, connect them up to the processing unit. Actually, you can run the connection automation. It will connect it all together for you automatically. And then you just write some software that actually configures that in the chain. So it enables certain elements, tells it the height, the width, the stride and such like, and it will just run through and kind of work. But eventually, you're going to want to create your own IP, which is where it comes in. And we could write it in VHDL or Verilog. Actually, it's a lot better idea to just go away and write it in for data processing things that we want to put in our Ultra96 side of things. It's much better to go away and write it in HLS if we can. So high-level synthesis allows us to work with C, C++, OpenCV. And it is a subset of C, so there are certain things that you can't use high-level synthesis for. You can't put system calls in there or accelerate libraries or anything like that. But generally, actually, it's not too difficult to take some C, think about it a little bit, read the rules a little bit, and then accelerate it and go away and create your own subsystem for this. You do need a little bit of awareness of what's going off in the hardware to get the best performance out of it, because you need to work out sort of a lot of loops that you might have in there, for loops, for instance. You might want to unroll memories, you might want to fracture, but it is quite straightforward. And when we work with HLS, it gives us a few libraries that we can have that will be accelerated into the programmable logic as well. So we have the math library. We can pull anything in that we want from the standard Vivado library as well. So if you've got FIR filters or FFTs or something that you want to do, you can pull that through. We've got linear algebra libraries, which are really quite useful, and arbitrary precision as well, which allows you to have random widths of bus So you're not stuck with 8 or 16, you can be more efficient in your hardware implementation, have 5 or 3 or 2. But for this application today, what we're really interested in is the 2 down the bottom, the revision acceleration stack, which really ties in with what Dan was talking about in SDSOC, and the Vivado HLS libraries, which are very similar. And that gives us the ability to work with sort of OpenCV type commands with slight changes to the namespace and a little bit of functionality, actually just quickly and easily implement embedded vision applications. So before I actually show you a little example of that, I thought I'd walk you through exactly a really simple example of what HLS is. So HLS essentially goes through 3 processes when it runs through synthesis. The first one is it works out what operations to perform on what clock edge. So it does the timing, it works out what the sequence of events can be. The second operation it goes through is it takes what it's worked out as a sequence of events, and it takes the operations that are going off then and attempts to bind it into the logic resources that are available in the programmable logic side. So it looks for things like DSP elements, memory elements, or what goes into the configurable logic blocks. And then actually the final stage is it does the control logic extraction. So there's not a huge amount in this example, but it will actually then work out it will then pull out the control logic to get the function working as you want it to. So in this example, it's a very simple example. It's got X, A, B, and C as inputs. It goes through the stages, and it works out that the tool works out it can do A, X, and B in one clock cycle, and then it can do the final one, addition of C on the second clock cycle, and then provide the result on the third one. So it goes through the initial binding, works out what operations are going off, and then it works out that it can add the first one to a DSP48 and the second one to a add submodule, which probably doesn't mean too much to you, but it's actually working out what can go into the programmable logic there and how it can be used. And that level of functionality actually allows us then to go away and start working with some of these libraries. So this is an example of a HLS image processing application that runs through, and in sort of 10 lines of code, you can run through and create a really simple Sobel filter that uses HLS to actually implement and drops an IP core into your processing chain in Vivado. You click build, and out comes the other side. So it's really quite simple. It's using pretty similar commands to what you see in OpenCV. Obviously, the difference is it's using the HLS namespace. But that's, so far in our application, really, we've talked about sort of you've got to build it with Vivado, you've got to create your own IP. What we really want to do is be able to actually do some system-level optimization and actually not really worry too much about what's in not do that segmentation ourselves, but initially develop the algorithm all in our language of preference, C, C++, or OpenCL, and then actually use a system optimizing compiler like SDSOC to allow us to move functions between the hardware and the software with ease. So SDSOC allows us to do that. We can move between, it works with the Zinc, the MPSOC, and obviously it works with Microblaze. And really what it means is we can spend the time where it's much easier to do it. So for instance, in C, we can write our applications faster, we can test it faster, but we might not get the functional performance we want. If we're doing an image processing pipeline, we might want 50 frames per second flowing through it. When we write it all in C and we run it on the APUs, we might not get that. But it allows us to prove out the functionality of it very quickly and very easily, and then we can then, once we've got that functionality and we're fairly happy that the algorithms are as we want them to be, we can then do some performance, we can analyze the bottlenecks, and we can start accelerating them from the running on the PS into the PL. And SDSOC allows us to do exactly that. And so the performance goes up, and the compile time goes slightly up as well. So you just have to go get a cup of tea or get a beer or something while it works. So this is the example step really, and it just allows you it shows you how you can iterate around from doing the system profiling to actually working out what your acceleration functions are and moving them across into the programmable logic. How it does this is actually really quite clever. Actually, Dan might have talked about this a little bit, but how it does this is really quite clever. So the first thing it does actually, it calls you've identified your functions that you want. It will call the Vivado HLS, so it will call the tool that I was talking about previously, the example I used for the Sobel filter. It will call that tool, it will go away, it will create an IP block for you. What it also does is at the same time it analyzes communication. So what you really want to do is move big chunks of data between the PS and the PL. You don't want to be sending sort of 10 bytes or 16 bytes, you want to be moving as much as you possibly can. the PS to the PL. Once it's analysed that communication, it works out how it's going to create essentially the communication interface that you need. So it's going to put in there the DMA infrastructure, the DMA engines that you need, and do that transfer for you. And then it's going to actually generate a new software stub. So whereas your function that you've accelerated was actually performing the function, SDSOC needs that function to actually now be there to drive the data on into the programmable logic and then pull it back out with the correct results. So it updates the software stub. So it's quite a lot going on under the hood, and it's really quite clever. I'll skip this one. Actually, no, I'm not going to skip this one. So what essentially it does is we can use it with Linux, we can use it with bare metal and FreeRTOS. What's really quite cool is you can use QEMU if you've got QEMU. You can run QEMU up and run an RTL co-simulation between the two. So as you can see, the two actually working hand in hand. And I think the latest version does have OpenCL. What I did actually on my blog is at FPGA Congress back this year, I ran a one-day course on how to do SDSOC. So all the slides actually, if you go to my blog site from that, if you want more introduction, are actually on there. So how it does it, I'm not going to step through all this, but how it does it is quite exciting. Obviously, down the block in the yellow down there, you've got your HLS IP component that you've accelerated. The orange-coloured elements are blocks that have been put in as part of the data communication path that's done from the communication analysis, and then the green blocks are blocks that have been put in there as part of the software, so it configures the DMA, waits for it to be done, calls the accelerator and such like. That slide should be animated, but I think it's gone slightly wrong in the Google Drive that we're seeing here. Come on. Oh, and it's broken now. So, I'm going to wrap it up here because we're kind of running a bit ahead. But if you want to accelerate things, obviously you need to think about what you can accelerate. You can't accelerate libraries and OS calls. There's a law called Armdale's law, which is a really great thing to use if you want to work out what sort of benefit of acceleration you're going to get from moving something from the PS to the PL. I've explained it a little bit more on that slide for anybody. I'll not read through it, but it's there on that slide for anybody who wants to read through and to work out what the actual equations are. But if you want to know more about this, because it's been quite rushed because we overrun a bit and we've had a few technical problems, but actually if you want to know more about how to use the Ultra96 in some of these applications, I've got a series of hacks to project showing how to use this, so from how to do the simple things such as how to create the Petalinux bare image literally from nothing and building it all the way up, or to actually updating the Petalinux image if you've done some builds. There's a couple of examples on there, some Internet of Things examples, and there's obviously my weekly blog that updates on how to use this. What's really cool though is next Tuesday, we've got a Hello Ultra96 getting started with a session, so free labs essentially going from nothing all the way through to sort of the bare metal approach, all the way through to creating web apps and running web apps on the Ultra96. That's next Tuesday at 8 AM, I think. And it's going to be really quite a good thing to actually do. There's a lot of people registered for it so far, so I'm quite looking forward to presenting that, and it'll be a lot better than this session, I promise you. And with that, guys, I'll try and answer any questions that you might have got. If not, we can all